Okay, 1172. Dinner plate stacks. You have an infinite number of stacks arranged in a row, numbered left to right from zero. Each of the stacks has the same maximum capacity. Implement the dinner plate class where okay, Roy pushes it to the leftmost stack, Pop pushes it from the rightmost stack and remove from the stack, and then Pop at stack removes it. Okay, yes. Hmm. Okay, I mean it's just uh, implementing an ADT. Let me see if there's any tricky things. I guess the tricky thing is you can't, or you shouldn't keep on pushing. Like you have to make some optimization to keep track of where to pop. And when you pop, I guess there's just a priority queue where you pop. Uh, I mean, push is well, yeah, you push until you can't anymore. But then when you pop, that's when you put in like a max heap or something like that, so that when you push, you don't have to like you know count each one along the way. I guess that's only it. I mean, pop. What's pop? Pop returns to rightmost. Okay, yeah. So pop is easy-ish. So okay, let's play around with it. Um, okay, it's capacity. Oh, the capacity of one stack. Okay, so I guess we should keep track of that. Okay, push. So we want a min stack. Okay. Oh, min heap. Uh, and then okay, maybe that's fine. And then just actual stacks. Okay, so push. How do we want to do the initial one? It's not that bad. Okay, let's just do, well, let's just do something naive and then we'll figure it out. Stack. So, okay, top is equal to if heap is equal to 0, then top is just, let's just say, well, it'll be just -1, right? And that's fine. Just make it explicit. Yeah, okay. And otherwise, top is equal to in heap, is it heap q dot pop? Okay. Otherwise, we push it to that stack. Let's go. Let's go. We have to add some checks. If top is less than 0, or top is greater than length of sub.stack. Then yep, we just want these are stacks anyway. Okay, that's my push, I think. And then pop, we just want to go. Okay, let's clean out the stack. And we pop the empty away, and then now the last one should not be empty. Then and then we turn -1 if all stacks are empty. Okay, actually we should check for that. If okay, and then pop it stack is just yes, as you go to so one, but then now we also want to do we want to push? Do we need to push the step out at the end? I don't check for one thing. I don't check for capacity, so I need to do that too. On the push, maybe the pop is okay. Okay, pop it stack. Well, if otherwise. But now we want to put this on the heap. Push. Okay. Something like that. But here we don't check. Okay. If the length is let's wait with it. I just separate these things out actually. If there's no min heap, then just take the last one. Okay, fine. Okay. Then okay. Well, that's not enough because we want to go to the next number then. because my idea here is that yeah, like here, I guess then the next one should be it'll go from 1 to 4, so this is not good enough. You pop another number off the top, maybe. 2 has no number. Maybe that's fine. What does this return? Okay. Now, if this is still true, then we have to get. Now we get do a 1. Okay. Let's run it and see. Oof. 23. What stack was a pen? Yeah. Oh, it's called heap push, and the other one's a heap pop. Oh, hey Taekwondo, good name, but also, yeah, I sometimes stream on other days, but I try to also stream on Sunday. So like that's like my, you know, my thing that I try to say. I do, but also welcome. Cool. Okay. I mean, so this it works for the test, but I'm also trying to figure out if like now is it good enough to submit? Don't know. Not really confident about it, but yeah, I'm lazy. Let's just do it. Okay. Well, how does that not get pushed? How? I guess this never happened. Wow. Well, now I get a test case, so I guess the example that they gave us was not really strict. Yeah. I try to do it every Sunday, and then once in a while I do it, but like during the week, but usually unannounced, to be honest. But okay, well, at least okay. Wow, that's actually surprising that I got it on the first try. Oh well, I mean second try, but that was just a typo that somehow the test can. Okay, but okay. I mean, it's not slow. It's faster than most or median or whatever. It's faster than half of the solutions, and it doesn't take that much memory, which I guess people use more memory. Cool. Yeah, pretty straightforward problem. Let's see, I took about 15 minutes, which is actually shorter than I thought I would, because I thought this was going to be a little bit more tricky with edge cases. Though to be honest, I was a little bit lazy near the end because I should have probably tested enough so that I at least got that one. But I thought there'll be more like randomness, but maybe this is enough. But my strategy or for this problem, I don't know how to, let me give me a second to articulate or think about how to articulate this in a good way. So I mean, push. I actually went back a little bit because push. There are a lot of it's very complicated as you can see. So I kind of was like, okay, let's think about how do I do the pop first. And the pop, the regular pop is easy, and that like you just go from the end out, the end in, the end toward the front. So I mean, and this code kind of illustrates that very straightforward, in a very straightforward way. I also get rid of empty stacks near the end just to make things easier for the future, at the cost of possible future memory allocation. But yeah, this is pretty straightforward. The pop at stack is the only place that is, that makes this problem different, which is that you could pop something in the middle, and what I did was now that know that I need to do that, I think about what I need for the push, and the push in this case is just you always want to push basically the leftmost or the smallest indexed to the smallest indexed stack. So that led me to think, okay, every time I pop at a stack, which is the only other operation in here that could make the middle stacks less than full, right? Because every other operation will fill it up or whatever. So that's why I put things in a min heap, so that that's that's the stack that you pop off at or push to when you push, and then I just do some extra little things around. Well, what if for whatever reason when you try push and it's already full, then you just get the next number, and I to be honest, I also didn't like. I thought this. I was hoping this would be enough, and I guess it was, but it didn't feel super. Like I wasn't super confident about it. I mean, I guess the invariant makes sense, but it's less that it's less that I didn't think this was right. It was more that I didn't think it was sufficient because I felt like maybe there's another sequence of events that could invalidate the invariant. So that it varies, I guess. But that didn't happen here, so that's kind of good for me. um, yeah, I mean, it's an interesting problem. I like it. Don't know how I feel. I mean, oh, and running time. Let's go over running time. So pop is just O of 1 because you always pop. I mean, there's some like amortize O of 1 stuff here for kind of cleaning up stuff. But it's always, you're only going to remove stuff once, so it's always going to be amortize O of 1. Pop at stack is O of 1 for the actual stack popping, but clearly there's a log of n for, and n is not the number of elements. N is, in this case, the number of stacks. So there's a log, the number of stacks on here for pop at stack, and push is O of log of n amortized for the same reasons. I mean, like, you're gonna get rid of some of these numbers, so it doesn't. So each thing on the min will only get used once, and if the stack is already full, you get the next one, but that only happens once, right? After you go for the min heap. So and each element in the heap is going to only be used only once, so each one at the cost of log the number of stacks. So yeah, so that's kind of the complexity analysis about it. Can you do better? Well, I mean, the only thing where you could, I mean, maybe there's some like the only way you could do best, I want to say O of 1, but you could probably maybe do some like crazy algorithms of log n, if you make some assumptions and split things up. But I think log n is probably okay because you can't really sort it. Yeah, because you could definitely pop at a lot of different orders, and each of them has 20,000 capacity. So definitely, yeah, I mean log of n is probably the way I would think about it. Yeah, as for kind of how likely is this on an interview and what would I look for, definitely maybe I would clean up some of this a little bit more. Definitely put everything into one function, but definitely I've seen more. I've seen interviews having more and more different abstract data structures to implement. So so definitely recommend that. Abstract data type. Sorry, yeah, to implement. So definitely recommend practicing this. And this one is relatively simple, kind of not super simple, but easy enough. Or like, well, let's just say it's easy enough to implement. You might not necessarily get the max stack, max heap thing immediately, but in theory, your interviewer could also give you hints on that. Let's see what it is. Yeah, yeah, okay, that's essentially what I did in a weird way. Maybe I could have done it a bit more, but yeah, that's what I have about this problem. I think. I mean, it's not too bad of a problem, and I think the tricky part with a problem like this isn't necessarily like knowing what to do. It's about like time management, especially like balancing between talking about a problem and fitting it into 45 minutes or an hour. I end up taking about like 20 minutes, but I also didn't talk very much as much as I used to do. Um, so so yeah, uh, but it's a good problem to kind of test, to I mean to implement. So and because you can play around with different trade-offs, and I think a seasoned interviewer would probably ask you like, oh yeah, what if I mean this is login and that's great, but maybe you don't need login, then what would you do, and how would you play along with it, and what are the data structures you could play with and stuff like that, and then kind of make you walk through the trade-offs. Um, yeah, okay, cool.